of numbers. In this video we discuss the Minkowski's fundamental theorem. The theorem states that if C is a two-dimensional M set with the center at the origin will be called O and have an area greater than or equal to 4. Then C contains either in its interior or on its boundary a lattice point of gamma other than the origin. C contains at least one lattice point other than the origin, which is not the origin. Here the property of the given set is that the set is an M set. The set is an M set, and it is centered at the origin. We know that an M set has a center. It's centered at the origin, and its area is equal to 4 or greater than 4. It's either equal to 4 or or greater than 4. So now we come to the proof of the theorem. Okay. We can treat the whole case into two. We can divide the whole case into two. In case 1, we assume that the given M set has an area greater than 4. And the second case that will be discussed in the last part of the proof of the theorem, which assumes that the area of the M set is equal to 4, and that case will be proved. That case, the result in that case, that the result will be proved using the using the proof of the first case. So we have two cases. In the first case, we consider the M set having area greater than 4. In the second case, we have we consider all M sets having area equal to 4. And the second case, proof of the second case will depend on the proof of the first case. So first, mainly we want to prove the to develop the proof in the first case. So for that, we consider an M set C with having area greater than 4 with its center at the origin 0 0. Now you can see that that M set in this figure. You can refer this figure. C is that M set having center at the origin. Okay. Next we do one thing, that we contract. We reduce the size of the M set. We contract C to C dash. We contract C to C dash by multiplying. How do we contract that? By multiplying the dimension of C by 1/2. Uniformly we contract it. You can see that when we contract C to a smaller M set having its dimension half of the dimension of a C, and this is the figure. Okay, and then you get C dash. This way, applying this method of contraction, we get C dash. Then that will also be an M set. Since we uniformly contract, we uniformly multiply all dimensions of C is multiplied by 1/2. So we get another M set, but a smaller M set having a center at the same point at the origin. It has the center at the origin. Okay. Then the area of you can say that then the area, what happens to the area of C dash then compared to the area of C? It will be then multiple of 1/4. It becomes 1/4 of the area of the original given M set, or the given M set. Okay, and that's given here. So area of C dash equal to A dash, equal to 1 by 4 into or a by 4, a divided by 4. Since a is greater than, we know that a is greater than 4. Since a is greater than 4, then a dash must be greater than 1. So this is the equation set 5.1. Next we place copies of C dash at every lattice point of gamma. In gamma we have lattice points equally spaced on the whole plane. It is filled with it is arranged with the entire plane is arranged with the lattice points which are separated in vertically, which are separated by at a distance by unit length, and horizontally also they are separated by unit length. Okay, and those lattice points we know that it is gamma contains infinitely many lattice points, and all such lattice point we arrange a copy of the M set, that small M set. Which M set? It is this small M set. We take the small M set, small M set C prime, C dash or C prime we take, and we then consider copies of those of the M set, of the same M set at every, which are centered at every lattice point. No lattice point is left without arranging that copy. At every lattice point we have a copy, we create a copy, and we call such M sets the translate of C dash. So we will call in our further discussion, we will call that they are translates. They are translate of C dash. Okay, then consider translate of C dash, which is placed at then after making this arrangement of translates at every lattice point of capital gamma, we consider a translate of C dash, C prime, translate of C prime, which is placed at the point PQ, which is placed at the point PQ. This is a lattice point. PQ is a lattice point, so P and Q are integers, which is placed at PQ as sender, which is placed at PQ as sender. P and Q are integers because it's a lattice point. Then the corresponding point of a point x dash y dash, which is in C prime. The point x dash x prime y prime or x dash y dash. See, you can see that here. Here you can see two M sets you can see here in this figure. The figure 2 you have to refer corresponding to this discussion. In this figure you can see the original M set C. Original, it is not original. That is the reduced the small M set. Small M set C prime, and which is centered at the origin. And we consider some point x prime y prime belonging to the M set C prime, and after that we take this M set to some new place, and that has sender at PQ, which is centered at PQ, but PQ is a lattice point. Then corresponding to this translation we have a corresponding point here in the new translate of C prime also. We have the corresponding, and we will call that point the corresponding point of x prime y prime in the new M set, and you can see that a point here, and you can easily write the coordinates of that point, coordinates of the new point, that is x prime plus p and y prime plus q. X prime plus p and y prime plus q is the coordinates of the new point. Okay, that is the things. These are the things which are explained here. Okay, next we move to the next point, next important part. Here we make a claim now. At this moment, at this point, we make a claim. Every translate, we claim that. What is the claim? Every translate overlap with here. This word is overlap. Okay, every translate overlaps with another translate, and this is our claim. See, every translate where are those translates? These translates are arranged here, arranged in the fundamental lattice gamma. In the plane, we consider all the lattices, all the M sets. We consider all the M sets which are all the translates of the M sets. All translates of C dash, C dash we consider, which are arranged on the plane. And when you take a particular translate, when you take a particular translate of C prime, you can see that translate will overlap with at least one another translate. So that is the stated as this point is stated here as a claim. So we have to we claim what do we claim here? We claim that every translate overlaps with at least one other translate. One another translate. Okay, and we now proceed to prove the claim. We want to prove this claim. Further, consider a square in the plane with. So it's the proof is a little bit lengthy, and so for that we consider a square in the plane. Okay, we consider a square in the plane with the corner points 0, 0, n 0, 0, n, and nn. N is some suitable integer. Integer means a positive integer. Here n is some suitable positive integer. Here we have to consider 0, 0. That's the origin, and then n 0. N 0 is a point on the x-axis, right? X-axis. Okay. Then 0 n is a point on the y-axis, and nn, it is a point that determines the vertex of the fourth vertex of the square. Now at this point, we have to refer a figure. We have a figure here given here. I am taking you to that figure. I am bringing your attention to that figure. Okay, we are going to that figure right now. But that figure is included. Yeah, here in this page. Here you can see a square here. Yeah. Here you can see in this figure you can see an inner square. You can see two squares actually. Two squares are there. One square is red colored, and the other square is here. Actually there are many squares, but this big square you can see. Here the points are 0, 0, then n 0, n n, and 0 n. And then considering these 4 points, you can think about a square, and that square is this big that inner square. That inner square has many lattice points inside it and on its boundary. So let's consider those lattice points. You can see 0, 0 is lattice point, next lattice point, which is at a distance of 1 unit, and there are another one, and likewise. You can see then just above that, after leaving a distance of 1 unit, just above, you have same number of lattice points. How many are there? Here you have n plus 1. So considering 1, 2, 3, 4, 5, and 6. For 6 units, there are 1, 2, 3, 4, 5. For 5 unit length, you have 6 lattice points. Anyway, you have to okay, and for suppose then this is then 0, 1, 2, 3, 4, 5. Okay, if you count the n here, so if you count 5 here, then you have 6 lattice points, right? When we count since we start counting here with the 0. Since we start here 0, 0, 1, 2, 3, 4, and 5. Okay. As a result, we can due to that counting from 0, you get the number n plus 1 lattice points on this on the line. Similarly, you have n plus 1 lattice points. So when the coordinate is n, and the first coordinate here is n, then you have n plus 1 lattice points. Similarly, here you have n plus 1 lattice points, and the same number of lattice points here are present on every line. So total number of lattice points, when we count the total number of lattice points belonging to that big blue square, is n plus 1 into n plus 1. Okay, the number of lattice points is n plus 1 to n plus 1, because the x coordinate here is n. If the x coordinate here is n, then you know that there exists n plus 1 lattice points on that line. So the same number of lattice points exists here on every line segment. Therefore, total number of lattice points belonging to the inner square is n plus 1 into n plus 1. Number of lattice points belonging to the inner square is n plus 1 to n plus 1, that is n plus 1 square. Okay, at all these lattice points, actually we are placing the same translate. The original the small translate is C prime, that you can see here. This is the translate C prime where we begin, and then after that we take copies of translates, copies of this M set. We start with this M set, and then we take copies of the M sets which are centered at each and every lattice point belong to the square, the blue square. Okay, you can see that in that arrangement of the M sets here in the figure. Okay. Now we can come back to the point, where we stopped, where we divert to the point where we divert. Okay, and this is explained here. Okay, this is the point from where we started moving to the figure, and then there are n plus 1 into n plus 1 lattice points enclosed by the square. Okay, and that's explained, and we consider the translate of C prime at each of these points, and some of the translates will have its portions exceeding the boundary. Okay, what about that? What is that? What does it mean? Okay, exceeding the boundary, you can see. Okay, I will show that. Before going to figure again, let's complete this statement, and we have to consider another bigger square which completely covers all n plus 1 translates. Okay, and now we have to go to once again we want to go to the figure. You can see that some of these translates you can see, and they leave the inner square, and this is the boundary of the inner square, but you can see that some of the translates occur outside that. Some portions of many translates. Some portions of many translates are outside that square. So now we are going to consider a bigger square. We want to consider a bigger square which include completely all portions of all of these translates. Okay, that square you can see here, it is drawn in red color. But the question is, how can we decide the size of such a bigger square? And that's the question here we want to answer. Now we ask the question, how can we decide the size or the dimension of that bigger square or the red square? How can we find that? Of course we can find it, and there is a way to do that by considering that's done by considering the first lattice, the first M set C prime, and then for that first M set, for this particular M set, what do we do? From the center we measure the distance to boundaries, to all the boundaries of we measure the distance to all boundary points of that M set. See, we measure, that means we measure the distance from this point to that point, or it's a boundary point from this point, from the very center to all the points on the boundary. We take that, we measure all those distances, and then we take the maximum of those values. We consider the maximum of the values of all the distances, maximum of the values of all distances that are measured from the center of the M set C prime to its boundary, and then this maximum value will be will be taken as S. Okay, and this S can be used to, and this S can be used the maximum value can be used to, okay, once again we want to finalize that what is that CS. See, let us be it is mentioned here, let us be the maximum of all the distances of the points in C in here, but they are talking about all points belonging to C prime, but actually that doesn't need, actually we want to consider all the boundary points, because the maximum distance will belong to only the boundary of C prime. That's a common it's a fact, it's a common understanding about every set, you know. So using that, anyway, you can say this way also you can say, there is no mistake. So for that we consider all points in C prime, and we measure the distance of that point from its center, and we take maximum of all those values, maximum of all the distances, and then from the here center of C prime is the origin, and we add this value. That value is taken as S now. We add this value to the dimension of the first square at all the four sides. Actually, we want to add it to all four sides. That you can see from the figure. Once we want to go to the figure, we want to refer the figure again, okay, before that, and then the square has a dimension n plus 2s and n plus 2s, length n plus 2s and breadth n plus 2s, and we can confirm that, and so its area will be, if the dimensions are n plus 2s, then its area will be n plus 2s, and n plus 2s is equal to n plus 2s square. Okay, let's go to the figure. You can see here what do we do, and first we find the value of S. After finding the value of S, you add S to this line. You add S to the side of the upper boundary of the inner square, upper boundary of inner square. On both sides actually you want to add. So in this direction you have to add S. Here you can see the length is, but there is a variation in this length. You feel that variation, but actually that variation is not allowed. The same distance you have to add. We add the S unit in this direction. We want to add S unit in this direction. So it was actually an error made while drawing manually. It's a rough sketch only. Actually the distance added here must be S. In the same way, here in the upward direction also we want to add S unit, and here also we want to add S unit. In the downward direction also you can see this is the lower boundary of the inner square, so we add S in this direction and downwards. So in everywhere you have to add, and what you are going to get as a result of this addition, this increase in the increase given in the dimensions, in the length and the breadth of that square, you know, we are going to get a new square. You know, you can write the coordinates of that of the vertices of the new square, the red square, as minus S comma n plus S, and here you have n plus S and n plus S, and at the lower portion at the bottom you have minus S, because here you have S 0 0. So since we take S unit to the left, we get here minus S, and since here we go downwards, minus S unit downwards, and we are getting minus S here. So you get minus S, and here you can see that n plus S comma minus S are the coordinates. So that you can verify. After a little thinking, you can understand that how do we get to the coordinates of the vertices of the new red square. And now it is clear the area. You are now clear about the area of the new square. That's equal to n plus S into n plus S, because one of the sides of the square is n plus S, and its area is going to be n plus S. N plus 2S the whole square. N plus S on one side, S on the other side. So n plus 2S is one dimension, and similarly n plus 2S is the other dimension. Thus we get n plus 2S the whole square as the area. And next what next? We are going to find an expression, and here you can see. Okay. Now we are going to think about the total area created by all the m sets. Total of the area created by all the m sets. Again, go back to the figure to explain it easily. See how many translates are there in this figure. It is clear n plus 1 translates are there. Sorry, n plus 1 into n plus 1 translates are there. So in along one line there are n plus 1, and here we have in this set n plus 1, n plus 1, n plus 1 likewise. N plus 1 repetitions are there. So n plus 1 into n plus 1 m sets, translates or m sets are there. Total, so we can, and each of these translates has area a prime, right? If you consider that, if you take that a prime as the area of the translate, you know that value is greater than 1. We know that. We have confirmed that its area is a quantity greater than 1. Okay, that's a fact. Yeah, keep it there, and we can write the total of. We can easily say about the total of the areas. What is the total of the area? Because each of these translate have same area. All of them have same area. So total equal to n plus 1 square into a prime, and that is taken here. In this expression, first you can see n plus 1 square into a prime is the total of the sum of the areas of all translates. From that value we subtract another quantity. That quantity is area of the bigger square. Area of the bigger square, n plus 2s the whole square, is subtracted. Now expanded, it is then first quantity is expanded, and then minus, and second quantity is expanded. You can see n square plus 4s square plus 4ns, and then it is then rearranged and simplified, and you can see that you get a prime minus 1 into n square plus 2 into a prime minus 2s into n plus what? Okay, plus the quantity and plus this quantity plus a prime minus 4s square. Its continuation is written here in the here you have a term. That term is written here, a prime minus 4s square, and actually this quantity is greater than 0. Why? It's because it's because we have an explanation for that, and it is here. It is written that it is greater than 0. It is greater than 0 because of a fact. Okay, not because of one assumption that we have made. So here you cannot write it without that explanation, without that assumption. We make an assumption, and at this point I am going to tell you about that assumption. Without that assumption you cannot write that it is greater than 0. What is our assumption? What is our assumption? Here our assumption is that for making it clear, go back to the figure. Here we assume that actually in this figure you can see many overlapping. You can see this these two translates, the two adjacent translates here overlap. These are the overlapping portions. Here these two translates here shows an overlapping portion. Actually the three translates here have an overlapping portion, and likewise there are many overlapping portions. But now we assume that for the time being, we assume that there is no overlapping of translates. Means one translate completely avoids all other translates. See, in this arrangement, each translate, I want to make this point more clear. In this arrangement, what do we assume? About this arrangement, we assume that we are going to make an assumption which is just against the picture. Actually, you can see in the picture there are many overlapping, but you just assume that. Now we assume that there is no overlapping at all. There is no overlapping. If there is no overlapping, when we add the area of all the translates, when we add the areas of all translates, that quantity will be Okay. If there are overlapping in the situation of, we just assume that there exist, or then they are overlapping. The translates are overlapping. When the translates are overlapping, when we add the areas, if you find the sum of the areas of all the translates, then that quantity will be much greater than the quantity will be greater than okay. Okay, it must be then greater than the area of the bigger square. Now once again come back to, okay, we want to make that point more clear. We add the translates, add the areas of the translates, not just adding the translate, we add the areas of the translate, and if there are overlapping, then there's a chance that, not a chance, if there are overlapping, then their area must be then greater than the area of the outer square, area of the red square, but here, by using a fact here about, we are not making, actually that was an error in my statement that I made, that we are not making any assumption about the overlapping. Actually, we can definitely say that the area, this quantity, the quantity which is written here, by this quantity is obtained by subtracting the sum of the areas of translates from the sum of the areas of the translates, where we are subtracting the area of the outer square. Outer square means the bigger square, and that is then after subtracting that, we get the simplified expression, and this expression, you can argue that this quantity is greater than 0. How can we argue that it is greater than 0? You can say that, but it is not always greater than 0. In all situations it is not greater than 0, but you can argue, logically you can argue that this quantity is greater than 0. For that, let's analyze this expression. We analyze this expression. You can see that this quantity, this is the first part, the first term in this quantity. In the first term, you have a prime minus 1. This a prime is greater than 1. A prime is greater than 1. So a prime minus 1 will be a positive quantity. Since a prime is greater than 1, in our first case, in the first case that we are considering, a prime is greater than 1. So this quantity we get a positive quantity, and that positive quantity will be multiplied by n square. So but this is a fixed quantity, since the m set has a fixed area. Since the given m set has a fixed area, then its reduced m set will also have a fixed area, but that quantity is greater than 1. So for that particular m set, this quantity a prime minus 1 is a fixed quantity, but it is a positive quantity. When this quantity is, you can see that in the first term this quantity is multiplied by n square, but the second term is 2 into, it's a positive, 2 into a prime minus 2s into n. And but you have the fact that a prime is a prime minus 2s it's a quantity, but it can be negative also. It can be positive or negative depending upon the values of the quantity a prime and s. Okay, but that is not a matter actually seriously affecting, which is going to affect our discussion or our argument. In this quantity, the positive value or negative value of the first and the second and the third term, the third term is a prime minus 4s square. That quantity can also be positive or negative. But these two quantities, the sign of these two quantities are not going to affect seriously, because if we increase sufficiently large the square, in this square, and this square, in this square we are considering n points here. In this square, you can actually consider a bigger square, and there is no restrictions on that. We are not restricted to include the number of lattices on this line. Actually, there is no restriction. We can increase the number of lattices. I mean that we can make n sufficiently large. Now, as we take larger and larger values of n, one point is there that the number of lattices will increase. Only that is the problem. But that is not a problem actually. And actually that will help us to prove that the quantity here obtained is positive. When we take n sufficiently large, what happens to this the first term? N square will be much bigger. As n square becomes very big, this quantity will gain a much higher quantity, and this the first term will be much bigger, and it will become a very big quantity. You can make it a very big quantity by sufficiently increasing n. Okay, and that quantity, the first quantity, then can cancel the minus sign or the minus effect of negative effect of the second and third term. As a result, by increasing n sufficiently large, you can make the whole quantity greater than 0. So we have to assume that there exists a situation. That this expression becomes positive, and we depend on that situation. We consider only that situation, and we then after that we move to the next step. So at this moment onwards, at this position onwards, we are thinking that we are going to consider that this quantity is positive. The reason I have explained, why do we think, or how can we accept the fact that this quantity is positive? Actually, always this does not happen, but there exists situation. Definitely there exists situation which can give us a positive quantity from the left side for this expression. Okay, that is the logic behind it. Okay, and that is explained here. Next, so the entire expression is positive when n is sufficiently large, and hence we get for sufficiently large that happens for sufficiently large values of n. It means that the total of the area of the translates. Okay, that is the situation. That means that when this quantity is positive, what happens when this quantity is positive? And this quantity represents the difference of it represents the difference of the sum of the areas of the translates, difference of the sum of the areas of the translates, and the sum of the and the total area of the red square or the outer square, bigger square, or the square which contains all those lattices. When this quantity is positive, that means we are subtracting in the area of the square which contains all the translates together. All the translates are contained in it. So when we subtract the sum of the area of that the square which encloses all the lattices from the total of the areas of all the translates, all the m sets, it definitely, you can say that at least one lattice point, since this quantity is positive after subtraction. If we see that the quantity is positive, then we have to say that sum of the translates has at least some point in common. See, sum of the translates, not all of the translates. I would like to tell only one thing, that sum of the translates, sum means not total, and sum of the translates will have some common points, some points common with some other translate. So that is the point. That is the conclusion of the discussion. Here we have to conclude that. That means at least some of the translates, some of the m sets will have some points, sharing points with some other m set. Okay. It means that total of the area of the translates, arranged at the lattice points in and on the boundary of the inner square is greater than the area of the square that completely accommodates all the translates. So two translates. What is the conclusion here? I would like to repeat that conclusion of the discussion. That is two translates translates must overlap. That's our conclusion. So we have to say that two translates overlaps, and we can then show that based on this, or moving further, depending on the fact that two of at least some of the translates overlap, you can show that all of the translates overlaps with at least one other translate. Remember, we are going to show that all of the translates must share some point with must have some common point with some other translate. Then we can show that every translate overlap with. In other words, we have to show that we can show that every translate overlaps with some other translate. Okay. Then consider the two, for showing this, consider the two translates having one common point. We consider, we know at this moment, we know that some translates, there exist two translates having common points or sharing common points. Okay, next we are going to show that, make the point clear that all translates have some points, some common points with some other translate. Okay, and for that we consider two translates having one common point, having at least one common point, and let the center of the translates be P1 Q1. You can refer this figure. You can refer the figure. Then you can see here two translates, and these two translates have at least one common point. The red colored point is the common point, and you can say about the center of the translates. Center of the translate, the first translate has center P1 Q1, and the second translate has center P2 Q2. Now you can obtain the difference. You can draw a vertical line here. Here you passing through this center, you can draw a vertical line. Here passing through this center, you can draw a horizontal line, and these two lines will definitely meet. These two lines will meet, and you can then obtain the distances, and this distance that distance is from this center to the meeting point, the common point of the lines, and that distance will be that distance is equal to P2 minus P1. You referring the coordinates of the sendays. The sendays are all lattice points. You can obtain the distance P2 minus P1. That's an integer. And similarly, you can obtain the distance Q equal to Q2 minus Q1. You can obtain the distance Q2 minus Q1. That's also an integer. So both are integers. P2 minus P1 and Q2 minus Q1. And then these are this is about the it's about the sendays and the lines drawn and the distances measured. Then every point in C double prime, C double prime is the name C double prime. Every point in C double prime, that is x double prime, y double prime, has a corresponding point x prime, y prime. It has a corresponding point x prime, y prime in C prime, such that x double prime equals x prime plus p, and y double prime equals y prime plus q. So if a translate overlaps with another translate, and then every translate overlaps with a second translate. How can we argue that? Okay, and that is that will easily follow, actually, because geometry itself, from the geometrical arrangement of the M sets, the arrangement of M sets itself makes that point very clear. It can make the point very clear. because and if there exists the translates, that point you can easily understand from by referring this figure. How can we prove that? How can we argue that? And since this translate has some point shared with some other translate, if you take a copy of this translate here, if you take a copy of the translate here, and you can find the sender, then you have a sender here. You have a sender here. A sender of that translate will also be here. And from that sender you can measure this distance and the distance upwards. So this distance from this sender, from the new sender, if you take the translate here, from this sender, from the center of the translate, you can measure this distance. That distance is p2 minus p1, and you can measure the distance q equal to q2 minus q1 upwards from that point. From this point, if you measure the distance p equal to p2 minus p1, and that's an integer, and from there if you measure the distance q upwards, you get a point there, and that point will be a lattice point. Another point will be a lattice point. You can see that point is, you can verify that it has coordinate. So assuming that this is the p0 q0 is the center of the new translate. So okay, after considering this translate and these two translates, and these two translates are the translates which share some point, and these two translates share some point, we know that. And assuming this, based on this assumption, by taking this, by looking at this translate, you can consider another translate, the third translate. These are the first two translates. Then you can consider third translate. And that translate is obtained by translating this M set to that position. This position, but that position has center at p0 q0, and from that center p0 q0 you can measure the distance p and q, and then obtain another lattice point here. Okay, that you can verify that that is a lattice point, because p0 and q0 are already integers, and then p2 minus p1 is added to p0, so it's an integer, and q0 is an integer. q0 plus q2 minus q1 is also an integer. Okay, and therefore, and what we can do next, since this is since the fourth point, this point is the new point is a lattice point, you can take a translate having sender at that new point, newly obtained point. So we can take a new translate having the sender, the fourth point as the sender, and that is the fourth translate. Definitely that translate, the third and fourth translate will share the same set of points. So as the first and two translates share some points, and the same number of points or similar kind of points will be shared by the third and fourth translate. So from this discussion, it is clear that every translate, if two translates, if there exists two translate which share some point, then we can say that every translate which belong to that arrangement, the entire arrangement, every translate will share its points with some other translate. Okay, and then depending upon you, based on this fact, using this fact, we consider the translate C prime. We consider translate C prime which is centered at the origin. Then that translate will also share some point with another translate C double prime. Okay. In a similar way, what happened here? The same way the things happen here, and you can argue that there exists sharing points, or the points shared by the two translates. So one translate is C prime, that is the reduced translate, and then another translate will there exist then, just as we created a translate. The way we created a fourth translate here, in the same way we can show that there exists a translate which shares similar kind of points with the translate C prime. Okay, and the new translate will be called C double prime. Let's now come back to our discussion. our discussion means our lines that we were going through. Okay, and every point in C double prime, that's x double prime, y double prime, has a corresponding point in x prime, y prime. Yeah, that's correct. It's correct. Every point in C double prime, that point is, now we consider that point as x double prime, y double prime. We'll have a corresponding point x prime, y prime, that belong to C prime, such that and there exists a relation connecting these 2 points. Actually, there exists a relation, and that relation is explained here. The relation is x double prime is equal to x prime plus p, and y double prime equal to y prime plus q. X double prime equal to x prime plus p, and y double prime equals y prime plus q, and that is taken as the relation 5.2. The relation 5.2. And so if a translate overlaps with another translate, so if a translate overlap with another translate, then every translate overlaps with a second translate. That's now clear. That point is now clear. Okay. Next we consider a point a double prime, b double prime, which is common to the translate C prime and C double prime. See, using that fact that every translate has another translate sharing some points, and after knowing that, after establishing that fact, that we consider these 2 translate which share their points, and and also we take a point which is common to both of the translates, common to these translates, and that point is given the name a double prime, b double prime. That is a double prime, b double prime, which is common to the translate C prime and C double prime. There exists a point, and also there exists a point a prime, b prime in C prime, such that, and then due to this fact that we have this relation here, this relationship, and due to that relationship we can say that there exists a point a prime, b prime in C prime, such that a double prime equal to a prime plus p, and b double prime equal to b prime plus q, and that's the relation 5.4. Since C prime is symmetric, symmetry is there. Now at this point we use the symmetry property of C prime. Since the M set C prime is symmetric, since the M set is symmetric, C prime must also contain another point. It must contain another point, that is the negative of the point a prime, b prime. Since a prime, b prime, the point a prime, b prime is in C prime, the symmetry of C prime says that its negative is also there. It's minus point. By minus point we mean minus a prime and minus b prime. Minus a prime and minus b prime is also contained in C prime. Since and now we use the convexity of the set C prime. Since the set C prime is convex also, the points joining, the line segment joining the points a double prime, b double prime, and minus a prime, b prime will be contained in C prime entirely. It will be contained in, because C prime contains a double prime and b double prime. A double prime, b double prime, a double prime, b double prime is a point common to C prime and C double prime. So a double prime, b double prime, this point is clearly in C prime. This point is clearly in C prime, and minus a prime, b prime is also a point in C prime. Thus we have 2 points. What are the points? A double prime, b double prime. This is the point a double prime, b double prime, and the point minus a prime, minus b prime. Both are contained in C prime, and we can say that C prime is convex. Since C prime is convex and these 2 points are in C prime, are points in C prime, the line segment joining the 2 points which are in C prime will also be entirely contained in that convex set. So the line segment joining that is entirely in C prime. Okay, and since the line segment is in C prime, then the midpoint is also is present in C prime. The midpoint joining that line segment. What is the midpoint joining the line segment? See, one end is this point, and the other end is this point. The a line segment joining these 2 points are taken, and then the midpoint will be equal to the sum. First, you have to add the x coordinate and then divide, or you have to find the average of the x coordinate, and that will be the average of the x coordinate will be the x coordinate of the center, and average of the y coordinates will be the y coordinate of the center. Center means here the midpoint of the line segment. We are writing here the midpoint of the line segment. The midpoint of the line segment therefore equal to a double prime minus a prime divided by 2, b double prime minus b prime divided by 2. And that is the relation 5.5. And where is this point now? And this point is in C prime. Okay, this point also is in C prime. Not that point. Very important. So using 5.4, and let's go back to the relation 5.4. Yes, this is the relation 5.4. Using the relation 5.4, here we can simplify this and get that a double prime, when this is taken to the left side, a double prime minus a prime equal to p actually. Then b double prime minus b prime equal to q. So we have the quantity p and q, and that can be substituted in the numerator here. So this becomes p by 2 and this becomes q by 2. And what is the consequence of this? We get that p by 2 q by 2, because this point is in C prime. This point is in C prime. So the point p by 2 q by 2 is also in the newly named point actually both points are same, and this point the same point, but it has given the new name p by 2 q by 2. We have identified it as p by 2 q by 2, and this point is in C prime. Okay. That portion is not visible. This is the what is explained here is p by 2 q by 2 is in C prime. And so the original M set having dimension. So the original M set having dimension 2 times that of C prime. And let's now think about the original M set. The given original M set, we are now going. I think better go to the first figure. It's better. Yeah, referring that first figure is will be a good thing. Now you can now compare this. See, we have discussions on C prime up to this point. We have all discussions about the M set C prime, and in this C prime we have obtained that p by 2 q by 2 is a point. We have proved that p by 2 q by 2 is a point in C prime. But this is actually the actual M set, actually obtained M set in the as per the theorem. As per the theorem, we have an M set, original M set, that M set having area greater than 4. See, in the first case we have its area greater than 4, and that M set is shown here. See, and that was then reduced its size to obtain C prime. How was its size reduced? It was multiplied by 1 by 2. Now we are going to multiply it by 2. Multiply what? Multiply the dimension of C prime by 2. Now in the reverse order, we multiply the dimension of C prime of the we are going to multiply the dimensions of dimensions of the inner M set will be uniformly multiplied by 2. What you are going to get? You are going to get the original M set. The point, you should note the point that C prime contains the point p by 2 q by 2. Then what happens to that point? Due to the multiplication of the points by 2 to obtain the original M set C, that point p by 2 q by 2 will also be multiplied by 2, and it becomes pq. P by 2 q by 2, the point p by 2 q by 2, which is now in C prime, p by 2 q by 2, which is now in C prime, will be multiplied by 2 and will become p and q, p comma q. and P comma Q will be present where? It will be present in the outer M set. Clearly that will be, it's because P by 2 Q by 2 is present in the inside in the inner M set. Due to that fact, due to that reason, you can definitely say that PQ is a point which is present either inside or on the original M set, the original M set C. Okay, thus we have at this point we have clearly the point P by 2 Q by 2. You know, P and Q are integers. We have shown that, we have verified that P and Q are integers, and these two integers together make a lattice point. P comma Q make a lattice point, and that lattice point is clearly present either in C or on C or on the boundary of C. Oh, that means it's a point. That lattice point is a point belonging to the given M set. So this is the point, very important position. We have reached an important position in our proof. So what about this point PQ? This lattice point PQ, it is other than the origin. P comma Q, the lattice point PQ is not equal to the origin. So we can now conclude that the original M set C contains at least one lattice point other than the origin. Okay, that's about the first part of the our first case. First part of the proof, I mean the proof of the first case. Next we are going to consider the second case. In the second case, you know, we have that M set, the area of M set is fixed, that's equal to 1. Area of the M set, given M set is C. We assume that, let's assume that the area of the M set C is equal to 1, exactly 1. It's exactly 4 area. In the first case it was assumed greater than 4. In the second case, we have the second case by assuming that area of the M set is equal to 4, exactly equal to 4. Okay, then we come back to the last part. In that case, what happens? It is then we now assume that it is we suppose that the area of the M set C is equal to 4. That's A is equal to 4. A is taken as the area of the M set, area of the given M set. Okay, that's equal to 4. And C contains also we assume that, we also make an assumption that C contains no lattice points. We assume that C contains no lattice points other than the origin. We also just assume that, we are not sure about that, we just assume that. We assume we take the area of C equal to 4, area of the outer M set equal to 4, and we just assume that this C contains, the outer M set contains, the original M set contains no lattice point other than the origin, but surely there is one lattice point, that is origin, because it is the center. So that is there, but we assume that it contains no other lattice point. Actually it does not contain other lattice point, or no lattice point other than the origin. Okay, then what happens? You can now, okay, if it does not contain lattice points other than the origin, all lattice points, you know, the entire plane is filled with lattice points. Origin is 1. Now if you go in any direction, anywhere, if you go, you will find a lattice point on this plane. That's very clear. You are very sure about that. It is filled with because gamma contains infinitely many lattice points. So okay, so what happens then if C does not contain lattice point other than the origin, if it does not contain any lattice point other than the origin, as we go outside and search, you can see somewhere in its near that M set, or near and around the boundary of the M set, the outer M set, you will be able to find some lattice points. Okay, here, I mean, somewhere here you will find a lattice point. You have to consider a lattice point which is very close to the boundary. Here we consider a lattice point, but inside there is no lattice point other than the origin. Okay, inside or on the boundary there is no lattice point other than the origin, but there exists lattice point outside. So you have to consider a lattice point which is very very close to the boundary. Okay, then what we can do, and it is definitely that lattice point definitely cannot touch the boundary. That lattice point, I would like to repeat, that lattice point, the lattice point which exits outside C, the lattice point which exits outside C cannot touch the boundary of C. If it touches the boundary of C, then our assumption is then wrong. Our assumption does not exist. It is against our assumption. I mean, it is then against our assumption. At the time, for the time being, we want to proceed with our assumption. Okay, for that you have to say that the lattice point which exists is outside the boundary. It's away from the boundary. So you will be able to find some distance from the boundary up to that to reach that lattice point. To reach the closest lattice point, you have to travel some distance from the boundary. Okay, at this moment, you can increase or you can enlarge this lattice point uniformly. Sorry, you can enlarge this. I have made the mistake. It is not lattice point. You can enlarge the M set. See, this M set can be enlarged by a slight quantity, by a very small quantity. Uniformly it will be enlarged, not in only one direction or two direction or three direction. It will be enlarged in all direction. It can be enlarged in all direction, but by a very very minute quantity, very small quantity. What happens then? Then its area will also increase. As a result, we have just assumed that area of C is equal to 1. Area of C is equal to 1. It's our fact. We are standing with the fact that area of C is equal to 1. So after enlarging C by a slight quantity uniformly, then you will get a lattice point. Sorry, you will get a new M set. Then you will get a new M set. It's not lattice point. Yeah, I am yes, I'm in between. Somewhere I wrongly say that an M set is lattice point. So you may note that that point. So it's a mistake made by fast explaining of the things. So it's an M set. We are increasing the dimension of that M set, and that will be a new M set. We can, by due to this enlarging of the dimension, then you can obtain a larger M set, a bigger M set, but you can still keep that that closest lattice point. That is a lattice point. This one is the lattice point, I mean, and that closest lattice point can still be kept outside that enlarged M set. Okay, now we come back to we would like to return to the last part. Okay, for then you can see, so we must correct the statement. Oh, then before that, so this is the point where we moved to, from where we moved to that. Okay, no, it is not there. Yeah, here, this is the point. Okay, next we suppose that the area of C is equal to 4, and that C is equal to 4, and C contains no lattice point, and we also assume that C contains no lattice point other than the origin. Okay, then you can see that, and there also we have constructed a figure, and in this figure 5 you can see that that origin, and then C, we have that original M set to C, and we then enlarge it, and also we take that the closest the nearest lattice point, the closest lattice point which is the closest lattice point to the boundary. Next we consider the boundary of the M set. From the boundary we measure the distances to all other lattice points in all direction. Then you can take the smallest value, smallest distance. There you will get a lattice point, and that lattice point can be called the nearest lattice point. A lattice point which is nearest to the boundary of the M set. but you can see a difference from the boundary, a distance. You can see a distance, a gap there. You can see a small gap there between the lattice point and the boundary, and that will help you to, that will make you to enlarge the size of the, or the dimension of the M set by a small quantity, very small quantity. But you should be careful about one thing, that it should not touch, this enlargement should not contain that lattice point. It should not be enlarged by a very big quantity. It should be very slightly enlarged, and so that it keeps that lattice point still outside that the M set, the newly obtained M set. You can see that newly obtained M set red colored, and that's given the name C prime. So in this new M set, let's think about the new M set. In this M set, already that has the has origin as the center. The new M set, C has the center as the origin as the center, and C prime also has the same center, origin as the center. But you can see that it still does not contain, C prime still does not contain any other lattice point other than origin. C prime does not contain any lattice point other than the origin, because still that L is outside. Okay, but what about the area of a C prime? Because of the fact that area of C is equal to 4 unit exactly, because of the fact that the M set C has area exactly equal to 4, and this enlargement makes the area of C prime just above 4. That means its area is greater than 4. Area of C prime is greater than 4. Now let's stop here and think about C prime again. Now C prime, we have C prime an M set. C prime as an M set, we have a new M set C prime, and its area is greater than 4. But this M set does not have any lattice point other than the origin. Okay, this M prime, I would like to repeat it again. I would like to repeat this M set. Which M set? New M set C prime. This C prime does not have any lattice point other than the origin. This entirely contradicts. It contradicts the proof of the first part. In the first part, what do we prove? We have proved that in the first part, or in the first case we have proved that if the area of an M set is greater than, if the area of an M set which is centered at the origin is greater than 4, if its area is greater than 4, then it must contain a lattice point other than the origin. But what we have obtained here in the second case, we have obtained an M set, its area is greater than 4, but it does not contain any lattice point other than the origin. It's a contradiction. So we have that contradiction only in the second case. We have obtained the contradiction only in the second case. What might have the reason for obtaining that contradiction? What is the reason for that contradiction? This contradiction might have obtained. It might be due to the loose assumption that. It might be due to the loose assumption that which assumption we have made about the inner M set. We have assumed that there is no lattice point other than the origin in or on C. We have loosely assumed that there exists no lattice point other than the origin in or on the boundary of C. That might be the wrong assumption that we have taken. So we have to correct that assumption. That assumption will be corrected. We will correct it and restate that there must exist. This happens only in the second case. So we will correct. We would like to correct the statement that there must exist at least one lattice point other than the origin inside or on the boundary of C, on inside and on the boundary of the lattice point, even if its area is equal to 1. Even if its area is equal to 1, that's very important. Okay, and by this we can conclude the proof of the second part also, the second case also. Thus, combining the proof of the both cases, case 1 and case 2, we have to say that whatever is the the area, if the area of a given M set having its center at the origin, if the area of an M set having its center at the origin greater than or equal to 4, if its area is greater than or equal to 4, then it's possible to find a lattice point. Then it is possible to find a lattice point other than the origin, either inside the M set or on the boundary of the M set, either inside or on the boundary of the M set. Okay, that's all. That's the end of the proof. Thank you very much.